Guess we can get started on counting and probability. Today we are going to cover two sections. Counting and probability, section 4, the pigeonhole principle first. The pigeonhole principle states that if n pigeons fly into m pigeonholes and n is greater than m, then at least one hole must contain 2 or more pigeons. This principle is illustrated in the figure here with f for n equals 5 and m equals 4. Illustration A shows pigeons perched next to their holes, and B shows the correspondence from pigeons to pigeonholes. The pigeonhole principle is sometimes called the strange German word or German name box principle because it was first stated by a German mathematician back in the early 1800s. So the pigeonhole principle states that a function from one finite set to a smaller finite set cannot be one-to-one. There must be at least 2 elements in the domain that have the same image in the codomain. In a group of 6 people, must there be at least 2 who are born in the same month? No, because there's 12 months. You can have people born in 6 different months and without duplication. But what about 13 people? Yeah, there would have to be at least 2 people that were born in the same month. Among the residents of New York City, must there be at least 2 people with the same number of hairs on their heads? Why? How many hairs are on the head? Yeah, you have to kind of know the population of New York and the number of hairs on the average person on the maximum number of hairs on a person's head. So we went through A already. B, the answer is yes. In this example, the pigeons are the people of New York City, and the pigeonholes are all the possible numbers of hairs on any individual's head. Call the population of New York City P. It is known that P is at least 8 million people. Also, the maximum number of hairs on any person's head is known to be less than 300,000. So you define a function h from the set of people in New York City to the set of the number of hairs on a person's head, and shown in this diagram here. Since the number of people in New York City is larger than the number of possible hairs on their heads, the function h is not one-to-one. At least 2 arrows point to the same number. And this means that at least 2 people have the same number of hairs on their heads. If nothing else, there's the fact that more than one person shaves their head. So, there's going to be more than one person that has 0. So, application to the decimal expansion of fractions. One important consequence of the pigeonhole principle is the fact that the decimal expansion of any rational number either terminates or repeats. A terminating decimal is one like 3.625, and a repeating decimal is one like 2.38246 with a bar over the 246, which means that those digits are repeated forever. Let a and b be integers and consider the fraction a over b, where for simplicity a and b are both assumed to be positive. The decimal expansion of A over B is obtained by dividing A by B, as illustrated here, for A equals 3 and B equals 14. And let R0 be equal to A. And let R1, R2, R3, etc. be the successive remainders obtained in the long division of A and B, A by B. By the quotient remainder theorem, each remainder must be between 0 and B minus 1. In this example, A is 3 and B is 14, and so the remainders are from 0 to 13. If some remainder, Ri, equals 0, then the division terminates and A and B has a terminating decimal expansion. If no R sub I equals 0, then the division process and hence the sequence of remainders continues forever. By the pigeonhole principle, since there are more remainders than values that the remainders can take, some remainder value must repeat. Rj equals Rk for some indices j and k where j is less than k. This is illustrated again below for A equals 3 and B equals 14. It follows that the decimal digits obtained from the divisions between Rj and k minus 1 repeat forever. In the case of 3 over 14, the repetition begins with R7, which equals 2, and equals Ri. And the decimal expansion repeats the quotients obtained from the divisors R1 through R6 forever. Generalized pigeonhole principle. A generalization of the pigeonhole principle states that if n pigeons fly into m pigeonholes, and for some positive integer k and km is less than n, then at least one pigeonhole contains k plus 1 or more pigeons. This is illustrated here with m is equal to 4 and n equals 9 and k equals 2. Since 2 times 4 is less than 9, at least one pigeonhole contains 3, 2 plus 1, or more pigeons. So the general pigeonhole principle formally is for any function f from a finite set x with n elements to a finite set of y of m elements, and for any positive integer k, if km is less than n, then there is some little y element of big Y such that y is the image of at least k plus 1 distinct elements of x. Show how the generalized pigeonhole principle implies that in a group of 85 people, at least 4 must have the same last initial. Well, in this example, the pigeons are the 85 people, and the pigeonholes are the 26 possible last initials of their names. Consider the function L from people to initials defined by the following arrow diagram. So, since 3 times 26 is a 78, which is less than 85, the generalized pigeonhole principle states that some initial must be the image of at least 4 people. Thus, at least 4 people have the same last initial. Consider the following contrapositive form of the generalized pigeonhole principle. For any function f from a finite set x with n elements, to a finite set big Y with m elements, and for any positive integer k, if for each element y of big Y, the inverse function of f of y has at most k elements, then x has at most k times m elements. In other words, n is less than or equal to k times m. I don't like the way that's presented. It's not very clear. And it's kind of confusing, but they don't present it in a clearer fashion in these slides. Proof of the pigeonhole principle. The truth of the pigeonhole principle depends essentially on the sets involved being finite. We know that a set is called finite if and only if it is the empty set, or there is a one-to-one correspondence from the set of 1, 2, 3, etc. to n, to it, where n is a positive integer. In the first case, the number of elements in the set is said to be 0, and in the second case, it is said to be n. A set that is not finite is called infinite. Thus, any finite set is either empty or can be written in the form x1, x2, etc. to x sub n, where n is a positive integer. And they restate the pigeonhole principle here. For any function f from a finite set x with n elements to a finite set y with an m elements, if n is greater than m, then f is not one-to-one. An important theorem that follows from the pigeonhole principle states that a function from one finite set to another finite set of the same size is one-to-one if and only if it is onto. This result does not hold for infinite sets. So theorem 942 states that let x and y be finite sets with the same number of elements, and suppose f is a function from x to y, then f is one-to-one if and only if f is onto. And what onto means is explained in either chapter 6 or chapter 7. I can't remember which. But if you do those extra credit chapters, you'll get an explanation of that. So, all right. That's section 1 for the day. So section 5 is counting subsets of a set. Combinations. Well, the number of subsets of size R that can be chosen from S equals the number of subsets of size R that set S has. Each individual subset of size R is called an R combination of the set. Definition. Let n and R be non-negative integers, with R being less than or equal to n. An R combination of a set of n elements is a subset of R of the n elements. The notation is the symbol big parentheses containing n over R with no bar like a fraction, which is read as n choose R. Denotes the number of subsets of size R for R combinations that can be formed from a set of n elements. So consider a set of 4 people: Ann, Bob, Sid, and Dan. Given the set, each subset of size 3 is a 3 combination of its elements. List all the 3 combinations of the set. Use the result of part A to find 4, choose 3. In how many ways can the people in the set form a committee of size 3? Well, each combination can be obtained by leaving out one of the elements of the set. There are 4 items in the list of 3 combinations in part A, so 4 choose 3 equals 4. The number of ways for the people in the set to form a committee of size 3 is the number of distinct such committees, which is the same as the number of subsets of size 3 and equals the number of 3 combinations of the set. Therefore, there are 4 ways people in the set can form a committee of size 3. There are 2 distinct methods that can be used to select R objects from a set of n elements. In an ordered selection, it is not only that what elements are chosen, but also the order in which they are chosen that matters. 2 ordered selections are said to be the same if the elements chosen are the same, and also if the elements are chosen in the same order. An ordered selection of R elements from a set of n elements is called an R permutation of the set. In an unordered selection, on the other hand, it is only the identity of the chosen elements that matters. 2 unordered selections are said to be the same if they consist of the same elements, regardless of the order in which the elements are chosen. An unordered selection of R elements from a set of n elements is the same as the subset of size R, or an R combination of the set. How many unordered selections of 2 elements can be made from the set 0, 1, 2, and 3? Unordered, so the order that you choose them doesn't matter. Close. 6. Yeah. So an unordered selection of 2 elements from the set is the same as a 2 combination or subset of size 2 taken from the set. This can be listed systematically this way. Since this listing exhausts all possibilities, there are 6 subsets in all. Thus, 4 choose 2 equals 6, which is the number of unordered selections of 2 elements from a set of 4. When the values of n and r are small, it is reasonable to calculate the values of n choose r using the method of complete enumeration. But when n and r are large, it is not feasible to compute these numbers by listing and counting all possibilities. The general values of n choose r can be found by a somewhat indirect but simple method. An equation is derived that contains n choose r as a factor. Then this equation is solved to obtain a formula for n choose r. Write all 2 permutations of the set 0, 1, 2, 3 and find an equation relating the number of 2 permutations and the number of 2 combinations 4 choose 2, and solve the equation for 4 choose 2. According to theorem 923, the number of 2 permutations of the set is equal to 4 factorial over 4 minus 2 factorial, or 12. That's the number of permutations. And if n and r are integers, it just restates it's theorem 923. Permutation of n and r is n factorial over n minus r factorial. So now the act of constructing a two permutation can be thought of as a two-step process. Choose a subset of two elements from the set and choose an ordering for the two-element subset. This process can be illustrated by the possibility tree shown here, where you have 12 permutations and 6 combinations. The number of ways to perform step 1 is 4 choose 2. The number of subsets of size 2 that can be chosen from the set. The number of ways to perform step 2 is 2 factorial. The number of ways to order the elements in a subset of size 2. Because the number of ways of performing the whole process is the number of two permutations of the set, which equals p of 4 and 2, it follows that from the product rule that p of 4 and 2 equals 4 choose 2 times 2 factorial. Solving for the equation for 4 choose 2 gives you p of 4 and 2 over 2 factorial. But we know that p of 4 and 2 equals 4 factorial over 4 minus 2 factorial. So substituting yields 4 factorial over 2 factorial times 4 minus 2 factorial, or 6, which is what is equal to 4 choose 2. So the computational formula for n choose r, the number of subsets of size r that can be chosen from a set of n elements, is given by the formula n choose r equals p of n and r over r factorial, or equivalently n factorial over r factorial minus n over r factorial times n minus r factorial, where n and r are non-negative integers, with r being less than or equal to n. Consider again the problem of choosing 5 members from a group of 12 to work as a team on a special project. How many distinct 5-person teams can be chosen? Quite a few, actually. It's a number of subsets of size 5 combinations, that can be chosen from the set of 12. The number is 5 choose 12, or 12 choose 5. By theorem 951, you get 12 factorial over 5 factorial times 12 minus 5 factorial. Do a lot of canceling out, do some multiplication, and you get 792 distinct 5-person teams. Use the multiplication rule to show that k of m and n, a complete bipartite graph on m and n vertices, has m times n edges. Use 2 combinations to show that k, a complete graph with n vertices, has n times n minus 1 over 2 edges. A complete bipartite graph, K, is a simple graph whose vertices are divided into two distinct non-overlapping sets, V with m vertices and W with n vertices, in such a way that there's exactly one edge from each vertex of V to each vertex of W, and there is no edge from any one vertex of V to any other vertex of V, and there is no edge from any one vertex of W to any other vertex of W. Think of constructing the edges between the vertices of V and the vertices of W as a m-step process. For each integer k from 1 through m, draw exactly one edge from vk to each of the n edges of W. Because each step can be performed in n ways and there are m steps, by the multiplication rule there are m times n ways to construct all the edges. Thus k has m times n edges. A complete graph on n vertices, k, is a simple graph with n vertices and exactly one edge between each pair of vertices. If n equals 1 and k sub n has one vertex and 0 edges, and since n times n minus 1 over 2 equals 0 when n equals 1, then k sub 0 has n times n minus 1 over 2 edges. If n is greater than 2, then since any two distinct vertices of k are connected by exactly one edge, there are as many edges as in k as there are subsets of size 2 in the set of n vertices. Oops. By theorem 951, there are n choose 2 such sets. And n choose 2 is equal to n factorial over 2 factorial times n minus 2, which simplifies to n times n minus 1 over 2. Therefore, k has n times n minus 1 over 2 edges. Poker. The game of poker is played with an ordinary deck of 52 cards. Various 5-card holdings are given special names, and certain holdings beat certain other holdings. The named holdings are listed from the highest to the lowest. Here. Royal flush, straight flush, 4 of a kind, full house, flush, straight, 3 of a kind, 2 pairs, 1 pair, no pairs. How many 5-card poker hands contain 2 pairs? If a 5-card hand is dealt at random from an ordinary deck of cards, what is the probability that the hand contains 2 pairs? Now consider forming a hand with 2 pairs as a 4-step process. Consider the 2 denominations for the pairs. Choose 2 cards from the smaller denomination. Choose 2 cards from the larger denomination. And then choose 1 card from those remaining. The number of ways to perform step 1 is 13 choose 2, because there are 13 denominations in all. The number of ways to perform each of steps 2 and 3 is 4 choose 2, because there are 4 cards from each denomination, 1 in each suit. The number of ways to perform step 4 is 44 choose 1, because the 5th card is chosen from the 11 denominations not included in the pair, and there are 4 cards of each denomination. Therefore, the total number of hands with 2 pairs is 13 choose 2 times 4 choose 2 times 4 choose 2 times 44 choose 2, or choose 1. Substitute that all out, do some canceling and multiplication, and you get 123,552 hands. But how many hands are there possible in all? Well, the total number of 5-card hands from an ordinary deck of cards is 52 choose 5, or almost 2.6 million. Thus, if all hands are equally likely, the probability of obtaining a hand with 2 pairs is roughly 4.75%. As a little side note, I have a little book. I should have brought it in today. I wasn't thinking about what we were going to go over today. It's called What the Odds Are. And it talks about statistics and probabilities of different events happening. And one thing that I ran across in there, it is more likely, marginally, more likely for you to die in your next car ride than it is for you to get a royal flush in a hand of poker. Yeah, it's kind of scary that it's that likely you're that likely to die in a car crash on your next car ride. What's slightly scarier is I've actually gotten a royal flush playing poker in Vegas. Yeah, so it's like I kind of beat the odds on that one. But you never know. You know, today's a gift. Tomorrow is not guaranteed. So yeah, there you go. Anyway, consider the various ways of ordering the letters in the word Mississippi. How many distinguishable orderings are there? Well, this example generalizes example 9.5.10. Imagine placing 11 letters of Mississippi one after another into 11 positions. Because copies of the same letter cannot be distinguished from one another, and once the positions for a certain letter are known, then all copies of the letter can go into the positions in any order. It follows that constructing an ordering for the letters can be thought of as a four-step process. Choose a subset of 4 positions for the S's. Choose a subset of 4 positions for the I's. Choose a subset of 2 positions for the P's, and then choose a subset of 1 position for the M. Since there are 11 positions at all, there are 11 choose 4 subsets of 4 positions of S. Once the 4 S's are in place, there are 7 positions that remain empty, so there are 7 choose 4 subsets of 4 positions for the I's. After the I's are in place, there are 3 positions left empty, so there are 3 choose 2 subsets of 2 positions for the P's, and that leaves just 1 position for the M, but 1 is 1 choose 1 is 1, so by the multiplication rule, you have the number of ways to position all the letters is 11 choose 4 times 7 choose 4 times 3 choose 2 times 1 times 1, or 1 choose 1, which multiplies out and cancels and all that fun stuff to be 34,650. The permutations with sets of indistinguishable objects. Suppose the collection consists of n objects, which n and each n of each different type are indistinguishable from each other. And suppose that n plus 1 plus 2, n plus 2, n2, n1 plus n2, all the way up to nk equals n. Then the number of distinguishable permutations of the n objects is n factorial over n1 factorial over times n2 factorial times n3 factorial, etc., to nk factorial. All right, some advice about counting. A group consists of 5 men and 7 women. How many teams of 5 contain at least 1 man? The incorrect solution is to imagine constructing a team as a 2-step process. Choose a subset of 1 man from the 5 men. Choose a subset of 4 others from the remaining 11 people. Hence, by the multiplication rule, there are 5 choose 1 times 11 choose 4, or 1,655 person teams that can contain at least one man. The problem of this solution, though, is that some teams are counted more than once. Suppose the men are Anwar, Ben, Carlos, Dwayne, and Ed, and the women are Fumiko and Gail, Huifan, Inez, Jill, Kim, and Laura. According to the method described previously, one possible outcome of the two-step process is Anwar from step 1, Ben, Gail, Inez, and Jill for step 2. In this case, the team would be right here, but another possible outcome is Ben for step 1 and Anwar, Gail, Inez, and Jill on step 2, which also gives the same team as before. Thus, this one team is given by two different branches of the possibility tree, so it is counted twice. So be careful how you count and that sort of thing. Now, the extra credit that I'm offering for the final, for 10 points on the final, this goes back a few years. They used to have a sign on the wall in Waffle House indicating how many ways you could have their hash browns with all the different toppings that they had. It was like 25 million and change different combinations for their hash browns. When I took this course many moons ago, I figured out how to count up the number of possibility combinations for hash browns at Waffle House, and it was larger than their number. Yeah, so it's more than 25 million. Well, that number is now useless because they've changed their menu and added toppings to their hash browns. So the extra credit question, worth 10 points on your final if you choose to take it and get it right, is to count the number of ways. Go to Waffle House, look at their menu, count the number of ways you can have hash browns at Waffle House. And show your work and explain how you got that number. And have an omelet while you're there. Why not? Waffle House is a good classic greasy spoon. It's a decent food periodically. I wouldn't live on it. Your cholesterol would be out the roof. But anyway, but yes, that's the extra credit if you choose to try it. And we'll see how many possible combinations there are for hash browns. Keep in mind, as far as that is concerned, there's the number of toppings, but there's also single, double, and triple hash browns. So count that in there too. I forgot to tell the other class about that little fact, but I'll try to remember next time. Yeah, well, that'll be it for the day. Like I said, we're probably going to take a couple of days off over the next couple of weeks because we're running ahead of schedule. We only have 4 sections left in Chapter 9 and 4 class sessions left. So we'll probably cancel. I'll probably cancel class a couple of times over the next couple of weeks. The final exam is going to be heavy on Chapter 9 because you're not going to have a test on Chapter 9. It's 3 questions each from chapters 1 through 5, and 5 questions from Chapter 9. So that is the structure of the 20 question final exam. I don't know the day of the day and time of the final exam yet. I need to look all that stuff up, and I will get back to you on that. But anyway, have a good day. See you on Tuesday.